Welcome to the Apache Sedona Community Office Hour for the month of May. My name is Jeff. Let's get started. So here is the agenda today. We're going to first briefly talk about the Sedona 1.9 release, which was released on April 22nd. And then we're going to talk about the upcoming SedonaDB 0.4 release, which is going to be out in late May or early June. And finally, we're going to have a guest talk. So Feng Zhang, who is the Sedona PMC member, gonna give you guys an overview about upcoming geography data type in Sedona Spark 1.1. As usual, I'll quickly go through the current status of Sedona. So Sedona is the most popular open source cluster computing engine for geospatial data at any scale. We have our website at sedona.apache.org. Also, we have our GitHub account, also on Apache. We have our social media account on X and LinkedIn, so be sure to follow us to get the latest news. And the Sedona ecosystem is going strong. There are many companies are using Sedona in production from different industrial sectors, including logistics, finance, insurance company, real estate, public sector, agriculture as well. The overall downloads of Sedona has exceeded 60, right now it is close to 60 millions overall. The monthly downloads of Sedona right now is about 0.5 million per month. Many people use Sedona. And there are over 150 contributors on GitHub. So if you'd like to join us, we welcome any kind of contribution to Sedona. Sedona support multiple different engines. It also have several sub-projects. So there is Sedona Spark. It runs on top of Spark. We also have Sedona Flink run on top of Flink, and also Sedona Snow. We also support small data. So we have a sub-project called SedonaDB, which is a standalone single node data processing engine for geospatial. We also have a sub-project called Spatial Bench. It is a benchmark that measures the current performance for a spatial analytical query engine. Here is the Sedona architecture. So this is about the Sedona Spark, the distributed system architecture. So we have three layers there. So the first layer of Sedona is the spatial query processing layer. It has spatial SQL, Python, and Scala, and R API. It also takes a distributed query algorithm, distributed spatial query input, and choose the best query algorithm. And we also have query optimizer that choose the best algorithm and operator for that. And the second layer is the distributed spatial dataset layer. So this layer decides how to organize geospatial data in a distributed cluster. So we have spatial partitioning, spatial indexing, and spatial data serialization. And all these two layers runs on top of multiple different engines, like I mentioned before. So it runs on top of Apache Spark for batch data processing, on Flink for stream data processing. On Snowflake, we also have Sedona Snow. But our support on Spark by far is the most comprehensive one. And also a quick overview about the SedonaDB architecture. SedonaDB is a new sub-project released last year in September. It is a single node analytical database engine with geospatial as a first-class citizen. So couple highlights here. It uses columnar in-memory dataset. It uses arrow and enables zero serialization, zero copy. It also does CRS tracking, spatial indexing, and spatial statistics. And we also have query optimization in SedonaDB, automatically choose the best query algorithm for different query. And the raster functions are coming soon in the upcoming 0.4 release. And if you want to try Sedona today, so here are some easy paths. So for Sedona Spark, you can just pull the Docker image and run it. And you will get Jupyter and Spark UI ready to use. For SedonaDB, you can do one single pip install, and with a few lines of Python code, you can just start to use SedonaDB. So both are very easy to get started with. So Sedona follows the 3 months release cadence. In particular, this applies to Apache Sedona. For SedonaDB and Spatial Bench, we are still working on a fixed release cadence, but because SedonaDB and Spatial Bench, they're both new projects, so it might actually have more frequent release. So for Sedona, we have released every 3 months. So we have 181 release earlier this year in January, and we have 190 release was done on April 22nd. SedonaDB had a release on February 27th, which is the 0.3 release. And Spatial Bench also recently had a release. It is the 0.2 release, which was released in February this year. Now, let's quickly go through the highlights of this Sedona 1.9 release. So I actually have covered most of the topics in the past community office hour, but here I'm just gonna briefly go through this. So 1.9 release came out on April 22nd. So this is a big release. This is a major release. So there are some highlights here. So first of all, we have the Spark 4.1 support. Now, Sedona Spark builds for Spark 3.4, 3.5, 4.0, and 4.1. So our Spark 3 support still runs on Java 11, and our Spark 4 support runs on Java 17. It requires Java 17. And the second highlight is the new CRS engine called Proj for Sedona. So this is totally new engine that is written purely in Java. So if you guys use the ST transform function or any or other raster CRS transform function in Sedona before this release, we mostly took an ESP3 number like 4326. And with this new release, with this new CRS engine, so you can now pass in full WKT1, WKT2 project string or even project JSON string. And also in addition to that, we also support a grid file. So now you can do very high precision datum shift through our grid file. You can actually pull datum grid files from Proud CDN. So there are lots of cool improvements we have done in the CRS side. Another cool feature is the native cog writer, cloud optimized GeoTIFF writer. So we introduced a new function called RS as cog. So this function turns a raster into a cloud optimized GeoTIFF. So cog, if you guys are familiar with that, it is great for cloud storage. It is great for, in particular, it is great for visualization directly out of a S3 bucket. You only need to read the part that you need, and also it comes with an overview, multi-level overviews that enables you to have nice visualization and a seamless visualization experience. Another cool feature is the bin tile function. So we introduced a full set of quite key tile functions. You can get a tile for a point, get all tiles for polygon, and more. So this function is introduced on Sedona Spark, Flink, and Snowflake. And the fifth, the new raster data source. So in the past, if you guys use the raster data source of Sedona before, so there's one downside there is, so it cannot read super large single raster image because there is a 2 GB record limit in Spark. So it disallows anything that is larger, any single record that is larger than 2 GB. And also, by loading this entire raster to the driver memory directly, so it will actually break the raster, break the driver memory. So this new raster data source, it does auto tiling for you. So basically, what it does is that with auto tiling, the raster data reader splits the raster for you on loading. So basically, it directly loads, assuming the data is originally stored in cog file. So it will directly load tiles and distribute tiles to workers in the cluster. So we don't actually load this entire image into memory anymore. So if you had issues before, feel free to try it out. And the sixth, new geometry functions. So there are a couple new functions: ST offset curve, shortest line, ST geohash neighbors, and the geom from MySQL. Couple cool features. So I won't go through individual one. And seventh, we also improved our GeoParquet support. We now write the covering metadata for the version 1.1, GeoParquet version 1.1 automatically. And we also support SRID round trip in GeoParquet through ProJSON. This way, right now, if you read GeoParquet into Sedona, you won't lose the CRS anymore. There are a couple other things. Finally, I think another important one is the GeoPandas compatible API. So as you guys probably already know, last year we introduced the GeoPandas on Sedona project. So basically, we enable any GeoPandas user to bring their GeoPandas workload to Sedona directly with one line change. Basically, if you did in the past, if you use import GeoPandas as a GPD, right? Right now you can use import Sedona GeoPandas.gpd. With the same code, with this one line change, the same code will be able to run on top of Sedona. So we keep adding more functions, more GeoPandas functions in Sedona. So in this release, we added approximately 30 new methods to have more function coverage of GeoPandas. So if you're a GeoPandas user or you have all the GeoPandas workload, feel free to bring that to Sedona. And if you want more details, you can read our release notes on the Sedona website. It has right now on Sedona website we have announcement. So if you are interested, click that. It will take you to the release note page. Cool. Now I'm gonna briefly talk about the SedonaDB point for release. Like I mentioned, SedonaDB is a single node database. It is purely written in Rust, and it is built on top of Data Fusion and Arrow. So, couple cool things here. So this list is still changing, right? We keep adding new features to SedonaDB. But a couple highlights here. So first of all, GPU accelerates spatial joins. So we GPU accelerates spatial joins. So the first feature is that in the past we have added lots of support for the spatial join in SedonaDB. By far, it is the most I would say it is the fastest spatial join engine, single node spatial join engine. And this is the first time we actually ship a GPU join in the core. So I'm going to talk about that later, give you more details. And secondly, another feature is the geography data type and also geography spatial join in SedonaDB. And third, the GDAL foundation. So basically, we also bring in raster support in SedonaDB. So this is something that we have been working on for a while. And this time it will be out in 0.4 release. We will have GDAL-based SedonaDB functions, raster functions. It will also have raster vector interoperability. So let's take a quick look at the GPU accelerate spatial join. So some context, spatial join is the most expensive operation in spatial analytics. So think about joining 1 billion points with millions of polygons, right? So on CPU, this will take time, and SedonaDB already does a fantastic job, but it is still taking time. So in the past year, so we have been studying how can we enable this to spatial joins through GPU. There are a couple efforts in the community or in the industry trying to do that. For example, there in NVIDIA, there is QDF, there is QSpatial. Unfortunately, library like QSpatial didn't actually understand geospatial challenges, right? So didn't actually speed up things that much. So eventually QSpatial now it is a dead project. So this time we introduced a brand new algorithm to actually support spatial joins through GPU. It is not through GPU CUDA core. It is actually through GPU's article ray tracing core. So look at the picture, right? So this is a brief overview of the GPU-based spatial join algorithm. So on the left, we have two sets of join. So the build set is polygons. The probe set is points. So in our GPU accelerated spatial join, so both sides are arrow batches in memory. So in the middle is this new spatial index trait. So before that, we always build a CPU R tree. Now, in this new upcoming release, you'll be able to pick a GPU index instead. So same code, it's just different backend. And on the right, there is a core, we call it lib GPU spatial. So this is our CUDA library. It is actually part of the SedonaDB repository. So if you guys are interested, you can take a look. So it has kernels for build, probe, refine, and filter on spatial relationship. And the result will come back as another arrow batch. So there are lots of new things to that. So when we're close to the release date of SedonaDB 0.4, I'm gonna bring more details here. Stay tuned. Another release feature is the geography type spatial join. So on the left of the picture, you can see that the globe with the S2 cells, right? So our spatial join, geography-based spatial join is basically built on top of S2 cells. So this way we can have much more precise spatial operation, assuming the surface is spherical. Okay. Another feature, the GDAL foundation, right? So look at the picture. Our GDAL foundation has multiple layers. So on the top, the user API, SQL, Python, R, and the REST crate, and in the middle, the Sedona GDAL layer. So the SQL, Python, R API is the place where, as a user, as a SedonaDB user, to interact with SedonaDB raster functions. So those raster functions is built on top of our Sedona GDAL crate. It has wrappers for dataset, rasters, VRT, and GDAL config. So we don't link GDAL at build time. We load whatever GDAL is on the user's machine. Another feature we're going to have is the raster and vector interoperability. So basically, raster files are large, right? So a single GeoTIFF can be hundreds of gig, and most of the time, user only care about a small area. So for example, so one city or one farm, but before point for release, so we don't have lots of raster and vector interoperability. So you can only load some simple raster functions, simple raster data, but you won't be able to perform any real operations on top of that. So we have been working really hard on that. And look at the picture right now. So right now with the upcoming point for release, so if you have a new raster, you can actually split that to many small tiles, and this green polygon in the middle is the AOI. We have a new predicate called RS intersect, RS contains, and RS within. So this enables you to connect raster data and vector data all together, allows you to filter those tiles based on the small polygon AOI. And we have several other operations following up. It will enable you to do more complicated operations such as zone statistics on top of the RS intersect result. Cool. This is a brief overview about point for release. Now I'll hand it over to our guest speaker, Feng Zhang, who is the Apache Sedona PMC member. So he will talk about the upcoming geography data type in Sedona Spark 191. Feng, please take over.
Okay, let me share my screen. Oh, I'm not able to share actually. Oh, okay, gotcha. Okay, can you all see my screen now?
Yes.
Cool. All right. Hello everyone. My name is Feng Zhang. I'm the Apache Sedona PMC member. So today I'm going to talk a little bit about like a upcoming improvement to Sedona. It is about the geography functions and joins that we want to support from 1.9.1. Okay, so first, like Sedona has been working with the geospatial analytics a lot. So we primarily focus on like geometry, like kind of type. So we have defined geometry UDT types, and also very early on we support geography type as well. So so these two types are the main like types that people in the geospatial domain mainly work on. Um, so yeah, we see a lot of people that are using both. We haven't like fully supported geography type in the past, but we do see some trend like people from a lot of different companies and industries. They are interested in have Sedona to support a more geography type because their use case are kind of more fit into geography versus geometry type. So, so if you, I believe a lot of you has already been very familiar with this topic, but if you look at the geography type, it's basically unique in terms of support. What kind of a use cases target mainly on like these three different categories. So first is like so the coordinate system is actually not uniform across the globe, right? So geometry is kind of use the planar per projections. So it's kind of distort the the geospatial domain that it's trying to represent. Like for example, one thing people see a lot of problems is around the region, um, across the anti-meridian region. For this region, the coordinates in geometry is actually not very. It is not a uniform transition that people. I mean, usually when you work with this region, the um, bounding box is actually very hard to get correct. So Sedona geography as a new feature, I mean, as an improved feature is actually targeted to solve this problem. Another is the distant measurement. Actually, in the real life, people use a geodesic unit like meters a lot instead of the degrees unit. So for this kind of a measurement, it's very hard to get that correct on the geometry type. So once we have more kind of like support from the geography type, it's very convenient, very, I mean, much more accurate to get the distance correct for for the real world use cases. Another one is the polar region support. We all know like the bounding box around the polar region, is very, I mean, it's very tricky. Like it's very hard to get it right, right? So because in this region, the planar representation of the Earth's surface is kind of distorted very much. So it's very hard to get the bounding box correct at that region. So with the geography support, they'll actually have a much better support on this. So why now? So geography has been used by a lot of people in the past, but in the last maybe a few years or very recently, we see a very clear trend that a lot of existing geospatial analytics ecosystem start to have more support for the geography type. Like this include the PostGIS, BigQuery, Snowflake, DuckDB. So Sedona as like a mainstream geospatial analytics. So we also want to kind of follow this pattern to basically have more support on geography type in this. So as Gia said, uh, right now we have SedonaDB. It's kind of the Rust-based and the native query engine. So we want both systems to support geography, and we're trying to maintain the function parity among different query engines for Sedona as well. So what do we have? What we will ship? Sorry, what we will ship in the next release will contain like two main parts. One's the ST functions. So before this release, we only support a very limited number of ST functions for geography type. But this release, we kind of add, I think, around 15 different ST functions for geography. This include spatial join predicates, ST contains, ST within, ST within, ST intersect, ST equals. So they are very useful not only for scalar transformation, but also for spatial join. So this will significantly improve our ability to do accurate geospatial join. Another is the measurement. So this includes ST distance, ST area, ST centered, ST buffer, and a lot of different conversations between different representations of the geography type. So we also support, the serialization format conversions between WKT, WKB, and the GeoHash. Yeah, so those are the upcoming geography type functions. So how to use it? So there's essentially no change in terms of how we use it because like 90% those functions has a pair for the geometry. So people should already very familiar with how to use that. The only they don't change how do they write SQL, how do they call their Python data frame API, and also Scala data frame API. All these are the same. So there's no change. The only thing is that now we support these functions to use the geography type as input. So yeah, so there's basically no change on the SQL, Scala, and the Python API. Okay, so yeah, I'm going to talk a little bit what under the hood. How do we build these features? So that's something a little bit new. So basically, I think there's two different things. One is the serialization format inside the Sedona. So when people load a geography type into Sedona, there's different ways people can represent them. They can use the raw WKB format. They can also use WKT, like some people do that, right? They just use or JSON formats or some other format that they can define. And also for geography, a lot of people use the S2 type of serialization formats. So for us, we introduced WKB geography as an abstraction on that. So basically, we want to support different type of serializations, but keep them lazily evaluated. By doing this way, we can support a very fast read, but only do the conversions when there's a need. So basically, this enables us to support different low-level libraries to do the geography operations, like the S2 library, and also sometimes we have to use the old GTS library. But with this lazily evaluation framework, we want to reduce the need to do a lot of conversions or unnecessary conversions on top of that. Okay. And also, so this is the first part, the serialization format to represent geography type. Another one is like a lot of operations, a lot of functions, and also joins need to build some spatial indexing on top of this raw data. So we also keep that as a lazy evaluation. So you don't have to create those spatial index on the shapes if there's no need. So that's also some kind of improvement for us uniquely to improve the performance on that. Yeah, so this is an example like how we do spatial joins on geography time. They follow exactly the same pattern as we do geography spatial join. Um, but the bounding box processing a little bit different. Um, so there's basically two sides, the build size and the stream size. Um, so right now we only support broadcast. So we haven't yet implement range join yet. So the build size will be broadcast. Like for example, in this sequence, let me close this. Yeah, in this example, basically you join countries with you join countries to airports. So the broadcast is the country's side. This is these are small regions. So as you can see, there's like the example have three different country shapes. So basically, we expand. We basically expand uh, the region that can cover these shapes um, by using some margin, so that you can have some kind of envelope to represent those smaller regions. And then we build a STR tree on top of that, so that we can quickly pruning we can quickly prune unnecessary like entries from the other side. So this STR tree on these envelopes are broadcast into each executors in your for the Spark cluster. So they can have when they get the build side, they would have the STR in tree index. So they don't have to redo by themselves. So on the streaming side, so basically they're trying, so there are two steps. First is they're trying to use this indexed bounding box tree to prune whatever they want to, whatever they want to do. And then there's a refined process to finally get the output raw, as you can see here. So it's pretty standard. The only difference is how we can extend the bounding box and how we can build S2 index on each of the geometries on the on demand. I mean, okay. So we did a little bit of benchmark for both the scalar functions and also the joins by using these new functions and join. So what we want to do is we want to compare using the same data set. What's the performance for a geography type versus a geometry type for the same type of data as well. And then when SedonaDB fully support this, we also want to compare on single node, like how Sedona Spark geography benchmark compared with SedonaDB once that's available. Yeah, so here are some of the preliminary results from here. So you can see on the left is a small scale, which means that we use a smaller data set. And then on the right is a median data set. They are evaluated against the different SD functions in terms of the join. So basically, we're using this predicate to do the broadcast join on different sides of the data set. As you can see, like the geography definitely is slower because it's much complex, right? It's trying to achieve more accuracy, but the trade-off is slower. So we're using using S2 geography library to do that. It's a very efficient library, but still it cannot beat the geometry type as for now. But we hope like SedonaDB can provide much faster performance on single node. But this is just give you some idea, like if you switch your joins from using geometry to geography, what kind of slowdown do we expect? So these are the joins. We also do Scala. Scala is much better than the join, because the join is really the additional computation for join is really you expand your bounding box more, so that you can you can do the filtering safely on the sphere surface. But the Scala, so they basically a little bit more computation for each ST functions. But for those very simple one, like the points, areas, so those are not too much. I mean, the types, ST distance, they are very similar to geometry. But for a little bit more complex one, like ST area, ST length, they kind of like double I mean, 50% increase or double the time need. Okay. So I think this is a very good first step to improve the geography supporting Sedona. We also do the same thing for SedonaDB. So that's also something we're trying to maintain the function parity between these two engines. But in the future, we also want to use these two system as a benchmark baseline to basically make sure every time we add new functions, every time we add new optimizations, we do see the improvement. So there's some benchmark work we also want to do. So I'm going to skip this because this pretty details on that. Yeah, so I think that's pretty much what I want to cover. I think this is a very good first step for us to have more support on geography type for Sedona and SedonaDB. But I hope like people like it, and if you are interested, you can contribute directly to the code base. Yeah, so yeah, I'm open to any question at the end. But yeah, back to you.
Cool. Thank you both. Great presentation. So as usual, folks, if you have any question, you can we have Q&A. You can also paste your question in the chat. So there's a question in the chat saying from Alice regarding the recording and the slides. So if you sign up to this webinar using an email, so we should be able to have your email. And I believe we usually send out our recordings through emails. So you should have received that, or you will receive one after the presentation today. And so in the past, I believe we probably didn't paste that to Discord. So sometimes I just forgot. So we'll continue to do that. So send our recording presentation to our emails and also share that in our Discord channel. Cool. All right. A few final things. So we have a free Sedona book from O'Reilly. It is about cloud native geospatial analytics with Apache Sedona. So if you're interested, you can find it. So Whereabouts is offering free copies. So if you search online, search cloud native geospatial analytics with Apache Sedona, it is O'Reilly book. So you'll find that on Whereabouts website. So we offer you a free copy. You can just go there and download that. I can also paste this link in the chat. And chat. Cool. Sedona is always calling for help. So we have a couple notebook examples on Sedona website. So if you have some better ideas of some really good demos you want to demonstrate, you want to contribute, so you can contribute those examples as well. And we'll contribute to Sedona, right? You don't always have to contribute to code example. If you find out there are some documentation typos and there are some improvement you want to make to the documentation website, feel free to participate. And we also have release testing. So every release of Sedona needs to go through a voting process. So members of the community needs to participate and check if there is an issue for each release. So if you're interested, you can join us as well. So this release testing always happens on our mailing list, file mailing list. So this is required by the Apache Software Foundation. So if you're interested, you can also participate in our release testing. And we oftentimes have a Sedona success story in live stream on LinkedIn and on YouTube. So if you want to share your story to the broader audience, feel free to reach out to me. And you can find me through email. So my email is jiayu@apache.org. And you can also find me on Sedona Discord. So we have, I believe at the moment, we have close to 700 members on Sedona Discord. So if you want to join the Discord community and talk to others, you're welcome to do so. Cool. That's it today. And thank you all for attending the community office hour for the month of May. So if you have any questions, you can paste in the chat. You can raise your hand, right? If not, so we can conclude today.